So, let us have another look at the simplex tableau. Let us see what is where. See here, these are the variables x2 to xn. This is your right hand side, the b vector, and then it always gives you the basic feasible solution. So, in the top row we decided to write C1 bar, C2 bar, the relative prices. Then this is your value of the objective function. This is minus, this value always reflects your minus z. Okay. Then let us assume that the first m columns are basic columns. So, you always have the identity matrix here, right. Then here you have your yj's, your, for example, these are the non-basic columns, right, and this is your basic feasible solution, B inverse B. Okay. Then if, see, as we saw, if you started with identity matrix here, and so you could read your initial few, that means your mostly if you have all slack variables added to all the constraints, then you will have identity matrix, and then you can read your basic feasible solution right away if your vector B is also non-negative. So, that will always give you B inverse, but this is not necessary, right, always. But what I am saying is that if in the beginning you could start with an identity matrix as your basic feasible solution, as your basis matrix, then because you started with an I and we are always pre-multiplying by B inverse, so therefore these columns will always give you the B inverse, and this can come in handy. Otherwise, we will, in any case, when we get a starting basic feasible solution, we will have B inverse with us, and then we can store it somewhere when needed. But basically I am trying to show you that this is your this thing, right. Now remember, our optimality criteria was that your Cj bar should be all non-negative, right, for all j, and we saw that the Cj bars for the basic variables are all zeros, and for non-basic variables they should be all non-negative. Now, it is possible that Cj bar is 0 for some non-basic variable, right. So, therefore, if you have a 0 here for a non-basic column, non-basic variable, your Cj bar is 0, then it is possible, if you can find, because this value is 0, I can enter this column also into the basis. The value of the objective function will not change, because remember, the change in the objective function value is given by Cj bar into theta, the level at which your variable xj will enter the basis, and this is the rate at which your objective function value changes, right. So, this is the total. So, if Cj bar is 0, the value of the objective function is not going to change, and that is what should happen, because we are saying that we are at an optimal solution. So, we have the best value of the objective function possible among all the feasible solutions. So, when Cj bar is 0 for some non-basic variable, there is a possibility of an alternate optimal solution, and that is what we are investigating here. So, the value of the objective function will not change. So, all I would need is some positive entry here, and if I have more than one positive entry, then obviously I will use the same pivoting rule, that is, I will take the ratios, enter the minimum one, right. That means I am just replacing one basic column by another basic column, and which I can do here, provided I have some positive entries here, and then I will have another basic feasible solution which will give me the same objective function value. So, I have an alternate optimal solution. And some time ago I proved to you this lemma, that if you have more than one optimal solution to your linear programming problem, then you have infinity of them, because every convex combination of the two optimal solutions, two basic feasible solutions, will give you another optimal solution, right. So this is another thing. So therefore you can have so optimality criteria. So if this is 0 for some this, then alternate optimal solution exists, right? And once there's more than one optimal solution, then there are more than there are infinity of them in the optimal solution, right? This is one. So now this should become very clear to you. This should sort of map into your minds, because we can then do a lot of things with the when later on post optimality analysis, even developing some other alternate methods of solving LPP, you would need this, right? Okay. Then another thing is that, yes, so as I told you that Cj bars are nothing but the rate of change. So therefore you can say that delta j by delta xj is Cj bar, right? So when for basic variables this is 0, and so what we are saying is that any increase in the basic variables will not change the objective function value, whereas this is this. So therefore when this Cj bars are all positive or non-negative, we say that we have an optimal solution, because the value of the objective function will only go up and not come down. So this is this thing. Then also you can see from here that your basic feasible solution, so if you want to yeah, so your value of z is Cb b inverse b. So this is a constant. So therefore if you want to look at delta z by delta bi, that means the rate of change of the objective function if the right hand side number is increased or changed. So this will give you this, and that will be Cb b inverse I. Okay, so that means this vector also has a meaning, and after a while I'll be able to give you very interesting interpretations of this quantity. And so this is the ith component here of this vector will give you the rate of change of the objective function with the right hand side, and much more sensitivity analysis we will do later on. Okay, so this is just to give you an idea of the simplex tableau, how it looks like. Okay, now let us come to another important aspect of this algorithm. See, in the simplex algorithm, we said that as long as your Cj bar is less than 0, there is a scope for improving the value of the objective function. Okay, but the algorithm as such does not specify. So let me write it out. What are the uncertainties or ambiguities in the algorithm? So one is the uncertainty about the variable to enter the basis. If you have more than one choice, then so two ambiguities in the algorithm, in the simplex algorithm. Right. So this is the variable to enter the basis. Okay, because as long as Cj bars, so here of course I told you that Danzig gave the rule to choose that Cj less than 0, which is smallest. Okay, fine. Suppose you fix this ambiguity and say that we will go for that variable to enter the basis for which the Cj bar is the smallest, negative. But the second one is, in case of tie in the minimum ratio rule, remember, no unique choice is given, the algorithm. the algorithm is silent about which one to choose. You know, you understand what I am saying. See here, when you have a column, suppose this is the one Cj bar is less than 0, you are wanting to enter this column, and on this side you have your xbi's, right. Then we said that we will look at the positive entries here, right, and then take the ratios. So that means we were looking at the ratios xbi upon yij, right, in this column. So this is for all yij positive, maybe I can say yij greater than 0. Now suppose it turns out that your smallest one xbi upon yij is equal to xbk upon ykj, right. These are the minimum ratios and the two of them are equal. So that means this one here and this ratio here. So you have your xbk. So the ratio here and here are the same, they are the smallest. Now which one should leave the basis? Anyone could leave the basis, right. So want to show you that even if you make this choice, even if you specify a rule for this, with the current choices given to you in the algorithm, it's possible that the algorithm will cycle, and I'll try to explain what we mean by the word cycle through an example. So in case of tie in the minimum ratio rule, no unique choice is given. So suppose we say that we will choose the variable with the smaller index to leave the basis, okay. So now I have fixed up both the ambiguities, unique choice for the variable to enter and a unique choice for the variable to leave the basis. So that means here, whichever see, when I say index, one has to be a little careful with the smallest index. What we mean is that see, remember there is an order for the variables, first basic variable, second basic variable, and so on. So in this case, if this is the third basic variable and this corresponds to the second basic variable, then I will choose the second basic variable to leave the basis, okay. So the smaller index variable should leave the basis, okay. Now suppose I have these two rules, and now let me show you what can happen, right. So this represents a tableau of a simplex problem, of a linear programming problem. Now right now the starting basis, yeah, so let me fix it up here. I'll just write down this way: A5, A6, A7 is the starting basis here, right, and we are going for the variable to enter the basis which has the smallest Cj bar. So this is your, currently this one is to enter the basis, and then here you see again you have the ratios, both the ratios are zeros, so there is a tie, and we said that we will, so this corresponds to the first basic variable, this corresponds to the second basic variable. So we will choose, according to our rule, we will choose this as the pivoting element, okay. So I pivot on this and I reduced it to 0, 1, 0, 0. The calculations are given here. So the second table, by mistake, first row got repeated as the top row. So now please make the correction. The top row actually reads as 0, minus 4, minus 7 by 2, 33, 0, 0 and 3. Cj minus Zj's are in the top row. By mistake, while in the lecture I wrote it as 1 minus 32 minus 4 36 4 comma 0 0. So the first line had got repeated. So please make the correction. This variable was entering the basis at 0 level, therefore the right hand side will not change. The value of the objective function also will not change because the variable is entering the basis at a 0 level. Okay. So this shows you the next tableau, and then here again we see that you have negative entries, and it turns out that this is the one with the smallest Cj bar value. So this will, and here of course you have only one choice because this is the only positive entry. So this will be your pivoting element, and your new basis will be, so after this your new basis came out to be A1, A5 and A7. Okay, fine. Right. So now we again pivot on this one. I make it 0, 0, 1, 0. Okay. Then this is the only negative entry. So this will enter the basis. Yes. And the ratio here again I will choose this because see, this is the first basic variable and this corresponds to the second basic variable. So the smallest index is this. Therefore, I will choose to have x1 or A1 leave the basis. Right, x1 becomes a non-basic variable. Okay, fine. So we do the pivoting here, and I come to this. So therefore, now your this thing will be A1, A2. I am always referring to the current basis. So A1, A2, and A7. This is your this thing. Right. Okay, fine. So now this is the tableau, and here again. This is the one which is this smallest Cj bar. So I enter this column into the basis, and the pivoting element here would be this again, because here this is the only one. This is negative, so I will be taking the ratios corresponding to these two. This is 0, this will be something positive. So obviously I choose that to be the pivoting element, and after the pivoting we reduced it to this form, right? And I have these entries here. So now this is where I will be able to apply my rule, that is, see, I have -1/2 and -1. The rule says that I should go for the most negative Cj bar. So therefore, this is the column which will now become a basic column, and the corresponding variable x5 becomes basic. And here the okay, I am short of space. So here what is the basis? Maybe we can write it somewhere here. Yeah, so corresponding to this I will write the basis. What was your basis here? A3, A2 and A7. Okay, corresponding to this. And remember, so that is why you always write the first column, first basic column, that means corresponding to 1, 0, 0, then 0, 1, 0 and 0, 0, 1. Okay. So pivoting on this, I get this, and here when you do this, so what is the corresponding basis here? The corresponding basis here is now A3, A4 and A7. So maybe I can write this way: A3, A4 and A7. Okay. So this is your new this thing, and now again I have this. Now here also you see -7/4 is greater than -2. Therefore, I will, by my rule, I will go for this column, and this particular variable becomes basic. So therefore, when you do this, the pivoting will be on this, and here, okay, sorry, we did not decide. Yeah, so here again the pivoting will be this. Yes, because 0/2 and 0/1/3. So tie, and therefore you go for the smaller index basic variable to leave the basis. So you pivot here, and therefore the corresponding basis here, when you did that, your basis was A5 and A4 and A7. Right. So when you pivot on this one, that means now A6 will again enter the basis. You see that? Yeah. And from here you will come back to this table. And this is what I am trying to show you, that after all, see, because at each iteration you had a degenerate solution, nothing was changing. Your basic feasible solution was not changing, your value of the objective function was not changing, but you had different basis representations. And this long ago when we were discussing a 1:1 correspondence between a basic feasible solution and an extreme point, I told you that there can be more than one basis corresponding to the same basic feasible solution, and in that case your basic feasible solution will be a degenerate one. So this is what is this phenomena we are seeing here, and that is that we continued changing the basis, and after we started with A5, A6, A7, and after this tableau I come back to, because A4 in this tableau, A4 gets replaced by A6, so I am back to A5, A6, A7, I get exactly the same tableau. And you see, if because I am following these two rules, if I now continue, I will again repeat the same sequence of basic feasible solutions and nothing will change. I will not move anywhere, I will stay with the same basic feasible solution, the same value of the objective function, but basis keep changing, right. So this is what is known as cycling. Okay. So we observe this phenomena. So this is a shortcoming in the simplex algorithm, and now of course the advocates for the simplex algorithm will say that this is a very rare case, and it is not that cycling will occur most of the time, but again if you are designing an algorithm, you have to make sure that all such pathological cases are also taken care of, right. So we observe the phenomena of cycling. So in the simplex algorithm, and this was of course discovered quite late, that simplex algorithm can cycle, and you saw that when you have degenerate basic feasible solutions, this is possible, right. So then came Bland. So now Bland in 1976 gave anti-cycling pivot rules, and not much needed to be changed, very simple this thing, but of course the proof required lot of effort. Okay, so what was the change he made? He says that instead of choosing the variable that has Cj bar the smallest, just choose, so he changed this thing to variable to enter the basis. Yeah, I will write so now the anti-cycling rule, okay, maybe I will write it here. The first variable for which Cj bar is then should enter the basis. This is the change he made. Don't go over the most negative Cj bar, just the first variable that you encounter. First, in the sense that when you scan this row, top row, looking for whether there is some Cj bar which is negative or not, then you stop at the first Cj bar which is negative and you enter. That means it will be the smallest index non-basic variable. Smallest index non-basic variable which should enter the basis if the corresponding Cj bar is less than 0. Okay. So should enter the basis, and the second rule is this. So second rule is this. So this plus this. So this plus this, these two together, Bland gave these two anti-cycling pivot rules, and he could prove. The proof right now for a first course is a little complicated, and we usually don't give it in the first course on linear programming. So anyway, you just take my word for it that he could, and you could see that here. In fact, what I will suggest is that as an exercise, see what did we do? This was the place where we had to use these two places. See, if here we had chosen this instead of this as entering this thing, then and then after that, if again we would have maintained Bland's rule, then you see you would not have cycled. You would not have come back to the same basis. Okay, so please sit down, and when you have time, just go try to do the pivoting. That means now you will enter this instead of this, then you will see that you will not cycle. So this was Bland's anti-cycling rule, and it proved very effective because now all the programs that are written for solving linear programming problems on the computers incorporate Bland's rule, because it makes sure that you are you will not cycle, and therefore at the end of the algorithm either either you will come to you will obtain an optimal solution, or the algorithm will tell you that there is a direction present and the problem is unbounded. So this is the understanding that we started with a feasible solution. So therefore our linear programming problem was a feasible one, and then continuing with this algorithm, we will either reach an optimal solution or we will discover that the problem is unbounded, and so we can stop there. So this is about the pivot rule. Now the second issue that we have is that you may not always be very lucky to get a starting feasible solution by inspection. So let me start on that now. And so once we make sure that we have a definite way of getting a starting feasible solution, the algorithm is all set, and we also have to take care of another assumption that we made in the beginning, that our LPP is feasible. That means our feasible set is non-empty. I started building up the theory based on the fact that our feasible set is non-empty, but now I will show you that we can do away with that constraint also, or with that assumption. So see, what I was saying is that in case suppose you have Ax less than or equal to B. Suppose you have a linear programming problem in this form, then I will add this and say that, right. So if all components of B are non-negative, I can immediately read my feasible solution as basic feasible solution as this equal to B, because then my basis matrix is identity, right? And in that case, remember my Zj quantity is Cb B inverse Aj. So since B inverse is so since B inverse is identity matrix, because B is identity, so therefore this reduces to simply Cbaj, right? And here for basic variable, this will simply be Cbi, the Zbi, right? So you have to write Cj minus Zj. So that means we will need just one single, yeah. So what will it be? Should I say Cbaj? And yes, right. Now what are your Cbs? For the slack variables, your Cbs are all zeros. So this is 0. Yeah, and for this is 0. So therefore my Cj minus Zj will simply be Cj. And for the basic variables, anyway, they are all slack variables. So the top row. So that means the top row is as we want, and the right hand side gives you the basic feasible solution. The tableau is also, because B is identity matrix, pre-multiplication by B inverse does not change anything. So I can just write the tableau as it is and start working with the simplex algorithm. Okay. But you may not always be so lucky. Your constraints may be greater, less kind, or equality kind. As I told you that we will mostly study the standard form of the LPP. So we need to have a mechanism for getting a starting basic feasible solution. So I'll give you first one basic thing here. This is phase 1 and phase 2 method. Okay, so phase 1 essentially gives you phase 1 is used for is used for computing a starting basic feasible solution, right. So what we do is we say that transform the problem to minimize psi equal to summation xai, I varying from 1 to m, subject to ax plus xa equal to b. So that means whatever constraints, whatever kind of constraints you have, I first reduce it to equality form, as I discussed with you right in the beginning, that by adding slack surplus variables you can always reduce the constraints to inequality constraints to equality constraints. And so I have an equality system. Now I want to I add artificial variables. So this are all non-negative. Okay. So this is the problem I will first solve. Now what are the possibilities here? When I apply the simplex algorithm to this problem, we know that psi is greater than or equal to 0 because all variables are non-negative. So this problem is actually bounded below. So there is no question of phase 1 LPP ever incurring the unboundedness criteria, right? Because the objective function value is bounded below by from 0, so it cannot be made as small as we wish. Psi greater than or equal. Now, so two things can happen. First, minimum psi is equal to 0. That means I am able to get when I end up with the simplex algorithm, I will either have minimum psi equal to 0 or to minimum psi greater than 0. These are the two possibilities, right? What happens when minimum psi is equal to 0? I should have said xai are the artificial variables, okay. And see, the name is very appropriate because this is artificially we are obtaining a starting feasible solution. And you can see from here also that if suppose in any feasible solution to this system, if an x corresponding if one of the artificial variables is positive, then what does it mean? That the regular variables will not satisfy that particular constraint as an equality constraint. So therefore, as long as in any feasible solution here some artificial variables are at positive level, then that solution cannot be feasible. That means if I drop the artificial variables and try to see if I have a feasible solution from among the regular variables, that will not happen. Okay. So therefore, and so the here what we are trying to say is that in case there is a feasible solution here from among the x's variables, then that means because I am minimizing this and the minimum value will be 0 provided no artificial variable is at a positive level. So in case there is a feasible solution here to the original system ax equal to b, then the minimum value here will not be positive. This is the idea. So you are using the simplex algorithm to find out a feasible solution to the original system by making a proper choice of the objective function. And these are the many other things that one has to learn to be able to see how in many ways you can use your simplex algorithm, right? Okay. So let's see what can happen when psi is 0, when the minimum value of psi is 0. So two things can happen. This is minimum psi is 0. Now, one, no artificial variable is in the basis. Okay. So no artificial variable is in the basis, then drop the artificial variables and the current optimal solution is a basic feasible solution for the original problem, right. So once I have a basic feasible solution, I can then switch off to the original problem. Okay. Well, maybe I should state somewhere the original problem I should have stated it. This is minimize Z C transpose X subject to AX equal to B. So once all your artificial variables are 0, I have a feasible solution for AX equal to B, and I can start with my simplex algorithm by replacing this objective function by the original objective function, right. Okay, what else is possible? Artificial variables are present in the basis, are present in the basic feasible solution, but at 0 level, right. So artificial, that means you have a degenerate basic feasible solution, and since the artificial variables are at 0 level, therefore this value became 0, the minimum value became 0, but I still do not have a basic feasible solution consisting of the original variables. Remember, the idea is to have a basic feasible solution from among the x variables. Okay. So basic at 0 level, right. So in this case, we would want to replace the artificial variables from the basis and get a basic feasible solution from the regular variables. Okay. So that is simple, because what is happening is, I again just use a diagrammatic this thing. See, the idea here is, so this corresponds to a basic feasible solution, to a artificial variable. So this is an artificial variable, and now see, if I have, as long as there is a non-zero entry in this row, I can do my pivoting on it, because remember, now the sign of this number is not important, since this number is 0. So the minimum ratio will anyway be 0, so I do not have to worry about the sign. As long as there is a non-zero entry here, I can pivot on that, and also I know that the Cj bar is greater than 0, but that is also of no concern, because the entering variable will be at 0 level, and I showed you some time ago that if the variable is entering at a 0 level, there is no change in the value of the objective function, right. So the value of the objective function will not change, it will remain optimal. So therefore all I need is that in this row I should have at least some non-zero entry. So as long as I have a non-zero entry, I replace the corresponding artificial variable, I get a basis from among the regular columns, right. If there is no entry, non-zero entry here, that means all are zeros. If all are zeros, that means in the original equation, original system, that particular row, that particular constraint is redundant, because all zeros are in the reduced system, one row becomes zeros. That means that row can be expressed as a linear combination of the remaining. So that means now the constraints are not all linearly independent, which was our initial assumption, but through this system we will come to know if there are any redundant constraints, we can drop them and start with the reduced system. So we can always replace the artificial variables and get a starting basic feasible solution from among the regular variables. So now let us demonstrate the phase 1, phase 2 method through this example. So suppose you have this linear programming problem to solve. This is greater than inequality, less than inequality. So I add here a surplus variable minus x4, a slack variable x5. Then I get the equality constraints. So I add xa1, xa2, because by inspection I am not able to find a starting feasible solution from this system. So therefore I just add the artificial variables xa1 and xa2. My phase 1 objective function is to minimize xa1 plus xa2, right, and all these. So now I can immediately, because 5 and 4 are non-negative, I can immediately read. In case suppose one of these numbers was negative, I would multiply it by a minus sign, because it is important that my right hand side should be non-negative, and then of course because I will add a slack or surplus variable accordingly, and add an artificial variable if necessary. So then my starting feasible solution, and so let us see, this is the first tableau which I have written out here. So this is my basic feasible solution, basic matrix. This is my basic feasible solution. Now the top row has to give me the relative prices, which are not right now available because I have to make these zeros. Once I make these zeros, then what I have here would be the Cj bars. Okay. So therefore, to do that, simply add the these two rows and subtract the sum from here. That gives me zeros here. The value of the objective function is 9, because if your xa1 is 5, xa2 is 4, the value is 9, and that will be minus there, minus of the objective function. So this is your Cj bar row, right? And I will enter, this is the only negative entry here, so we will enter this variable into the basis, and this will be my pivot element, right? Okay. So then you see that by making this as 0, 0, 1, 0, 0, 1, I do the pivoting. This is what I get as my next basic feasible solution. The value, okay, because this is 1, I don't, because this is already 0, 1, I don't do any, in fact I simply make a 0 here, I don't need to do anything here. Yeah, which reminds me that yes, we could have used the fact that this is a unit vector. So I should have added only artificial, but anyway, I wanted to show you the phase 1 method. So therefore we added artificial variables to each of the equality constraints. Right. So here I don't have to do any pivoting except that add this row to this row to make a 0. So that gives you the new Cj minus Zj, or the Cj bars, right? And again, this is the only negative entry. So this is the column which will enter the basis, and your x1 becomes a basic variable. So then here, of course, the pivoting would be, this is the only positive entry. So this is the pivot element here. Next tableau, when I enter a1 into the basis. So this is your basic feasible solution, and your value of the objective function has become 0. That means your min psi is 0 now, right? And therefore I have arrived at a situation where, and none of the what are your basic variables are x1 and x5. Basic variables are x1 and x5. So there's no artificial variable in the basis, and so I'm fine. My phase 1 ends here. So end of phase 1. This is end of phase 1. Okay, this is end of phase 1, and I can begin by my phase 2. That means I can now begin solving the original problem. So the basic feasible solution for the original problem is available, right? Now the thing is that I'll have to, now this is, remember in the beginning I showed to you that since this two columns made up my identity matrix, at any iteration what I read in these two columns would always be my B inverse, because remember I am pre-multiplying by B inverse. So this is my basis inverse, the current basis inverse, and to start the original problem, that means to start solving this original problem, I need my Cj bars. And so what is the definition? So this will be, for example, so C1 minus Cb B inverse A1, which of course here this is a basic variable, so this is going to be 0. I know it, I don't have to, but so if you want to compute for C2 minus Cb B inverse A2, you want to compute this C2 bar, and this will be your C2 is what? You will go back to this thing here, this is minus 3 minus, now what is your Cb? Your Cb, because your basic variables are x1 and x5, so Cb is, what is the this is 3, and x5 was a slack variable, so that was 0. So this is your Cb, right? And B inverse A2, you know, B inverse A2 is this column, y2, right? So minus 3, and this is 3, 0, and 2, 5. Yes, I am showing you the calculations in detail. It's a repetition, but anyway, it doesn't matter, because then it will become clear in your mind. So this is minus 3 and minus 6, so minus 9, which is less than 0, right? So that means here this will be minus 9. This is 0 minus 9, right. Then A3 is another thing, so I need to compute C3 minus CB B inverse A3, okay, which is, what is your C3? C3 is plus 1, so 1 minus, and this is 3 0, and B inverse A3 is minus 1 minus 2, minus 1 minus 2. So this is equal to, yeah, what will it be equal to? Plus 3, because this is minus 3 plus, so that will be 4, which is positive. So here this becomes 4, right. So C4 minus CB B inverse A4. So C4 is 0, 0 minus 3 0, and B inverse A4, B inverse A4 is minus 1 minus 3, minus 1 minus 3. So this is 3, which is greater than 0. So this is 3 here, and finally I don't need to do it for this. X5 is a basic variable which will also be 0 here. You can verify the computation, it will be 0. So you see, now I have new CJ bars, everything else is the same. So I can just remove this, I can get rid of this, okay, but I'll leave it. So therefore you can start your phase 2 from here, right. Maybe let me just do it for you here. So what will it be now? X1, so this is your phase 2, phase 2. So X1, X2, X3, X4, X5, that's all I need. The artificial variables have done their job, right hand side, and your new, this thing is 0, minus 9, 4, 3, 0, and this value X1 is 5, so this is 15, this will be 15. Yeah, you can verify that. You can again, because your Z is CB B inverse B. So just make the computation and see that this is 15. But I'll show you in another way also. Fine. This is this, right? And the rest of the tableau as it is 1 0 2 5 minus 1 minus 2 minus 1 minus 3 and 0 1, right. Okay, and your basic feasible solution is 5 and 19. So this is your phase 2 starting tableau, and we will now, since this is negative, the solution is still not optimal, we need to work for it. So this will be the entering variable, and 5 by 2, so this will be your pivot element, right. Okay, so let's quickly do the computation here. This will be okay, yeah, a little bit of 1 by 2 1 minus 1 by 2 minus 1 by 2 0, and this is 5 by 2. Now you want to make a 0 here, so 9 times this I have to add. So 9 times this will become 9 by 2, this is 0. 9 times, so 4 minus 9 by 2 would be minus 1 by 2. Then 9 times 3 minus 9 by 2 would be minus 3 by 2, right, and this is 0 because this is 0 here, and then 9 times this you are adding. So, oh, somebody should have corrected me, this is minus 15, right. Okay, so 9 times this, so you need to compute minus 15 plus 45 by 2, which is 15 by 2. So 15 by 2, okay, fine. And now I want to make a 0 here, so 5 times this you have to subtract. So this becomes minus 5 by 2, 0. 5 by 5 times you have to subtract. So plus 5 by 2 and minus 2. Minus 2 and plus 5 by 2, right. Then plus 5 by 2 and minus 3. So that will be minus, this is half, okay. And this remains as 1. And 5 by 2 you are multiplying by 5. So 25 by 2 is subtracting from 19. So 19 minus 25 by 2, 38. So 13 by 2. Okay. If there's any error, you can make sure. Fine. So now this is our new tableau, and what do you see here? That corresponding to this, of course, you might say that since we are applying Bland's rule, I would enter this, and so I would not look at this, but just to make the calculation short, I agree. We would enter this, but the thing is that you see from here this is negative. That means this column, corresponding column, can enter the basis, but the entries here are all negative. I cannot proceed with the simplex algorithm, and of course this is your unboundedness criteria. But you this is the objection would be valid in the sense that I may not come to this right away. I will first go here, and when I enter this unboundedness condition will persist, because there is a direction present in the polyhedron in the feasible region. So I will detect it at some time. Yeah. So right now, just to cut the argument short, I am saying that you see under this column you have, this is a profitable column, but the entries are all negative. So therefore the problem is unbounded. So we can stop here. Right. Now what I want to say here is just one improvement on this method is that, see, you remember, we need the, after phase 1, I need the Cj bars corresponding to the new object, corresponding to the original objective function. So why don't we just carry? So let me just quickly show you that if I carried my, so this will be 3 minus 3 and 1, this is 0 0, right. If I carried this objective function and I did the same operations, that means when I so here this was, yeah, so then what we do, we added the last 2 rows and subtracted from this. So let us do it for this also. That means when you add these 2 rows, this is what equal to minus 2. When you add, this becomes minus 2, and you subtract, so this becomes 5, right. Then plus 1, so that becomes minus 4. Okay, this is 0, so this does not change. This is minus 1, and so that becomes 1, and that is 1, so that is minus 1, right. And then the objective function value here would be also minus 9. Would it be, because I am adding this thing? Yeah. So this is what is happening, right. That is what I am saying. So whatever pivoting you are doing, you do with this, carry the second objective function also, so that when you are ending with phase 1, you can simply remove the top row and continue with this thing. So let us just verify that the what I am saying makes sense. So now when you are pivoting here on this one, I will make a 0 here also. Yeah, because I made a 0 here and this, so therefore you again add this row to this row. So what will happen here? This entry will become 2 per readable. So you are simply adding this row to this one. So that becomes 2. Then you adding here. So this is minus 5. This is 2, and this is 1, and this is 0. Right. So the last row you added to this one. So that becomes minus 5, right? Because you added the last row to the this one, and therefore that is also minus 5, right? Okay. Then what did we do? We pivoted on, yeah, we pivoted on this one, because this was minus 1. So here again I'll make a 0. So to do that, I'll have to add twice this, multiply this by 2 and subtract. So just do that. Twice if you do that, what will you get? Twice 2 minus 2, 0. You get 0. Then 4, so minus 4 minus 5, you get minus 9, right? Then minus 2, and you subtract, so therefore becomes plus 2, that's 4, and similarly 3. And the value here would be, what we got was, what was the value? Minus 15. Because twice 10 you subtract, you already had minus 5, so minus 15. So this is the idea. So then you can make your algorithm, because you don't have to do these extra calculations. So we carry both the objective functions, making sure that this corresponds to phase 1 and this corresponds to phase 2. Once we are done with phase 1, we can remove the top row, drop the artificial variables and continue with the phase 2 algorithm. Okay. Yeah, another point which again, since we are talking of, see, when you have an algorithm, you don't want to leave any loose ends, in the sense that what other things can happen. So let me now conclude about phase 1 and phase 2. As I had been pointing out in the beginning also, that when the problems are very large, you have no way of just by looking at the problem and saying whether it has a feasible solution or not, what is the rank of the coefficient matrix. So mostly all the software that are designed for solving linear programming problems have phase 1 and phase 2 built into them. Phase 1, as we said, obtains for you a feasible solution, a starting basic feasible solution, if there is one in the if there is one available. So we saw that the two cases were there. In fact, yeah, so phase 1, we saw that if psi is 0, then we know that okay, the problem is feasible because all the artificial variables are out of the basis. Then of course there were again two cases possible here, that are some artificial. So case 1 would be that artificial variables are out of the basis. So in that case, I have a basic feasible solution from among the regular variables, and so I will continue with phase 2. Or the other case would be that artificial variables are in the basis, but at 0 level, right, because the value of the objective function is 0. So, so the artificial variables are in the basis at 0 level. Then I showed you how you can try to replace the artificial variables by the regular variables by doing the pivoting, linear simplex pivoting, and you should be able to replace all the artificial variables. There can be a case when you have corresponding to an artificial variable which is at 0 level in the basis, and then there are no see, remember, to replace an artificial variable at 0 level, you just need some non-zero entry in this row corresponding to the regular variables, so that you can do the pivoting and get rid of this artificial variable from the basis. But in case there are no non-zero entries here, then of course you can conclude that this constraint, because if you remove this column, then all the elements in the row, in the transformed row, are zeros, and therefore you know from your linear algebra theory that this row this constraint is redundant, because you can express this row in terms of the remaining rows of the matrix, and so this constraint is not required, it is redundant. So therefore now you see phase 1 at the end will either give you a basic feasible solution from among the regular variables, or it will tell you that there is a constraint which is redundant, or more than one constraint redundant. And of course the third case is when you have psi greater than 0, then you know that the problem is infeasible. Right, the problem is infeasible, and we also said that since psi is required to be non-negative, since all the artificial variables are non-negative, so their sum will always be non-negative. So the unboundedness criteria will never be satisfied. So that means now whatever we had started with the assumptions we had made in the beginning to build up the simplex theory, we can now we don't need any of those assumptions, because our phase 1 and phase 2 will tell you whether the problem is feasible or not, and if it is feasible, are there any redundant constraints. We can remove those redundant constraints. That means we don't anymore need that the rank of the coefficient matrix must be equal to m. We will know which are the redundant constraints, we can drop them, and then so and the reduced matrix will again be a full rank, or you will know that the problem is infeasible. So the unboundedness criteria will not be satisfied. Then we start with phase 2, and then phase 2 will of course either give us a finite optimum solution, or it will tell us that the problem is unbounded, because then phase 2 we are back to the original problem, and so you will know at the end whether the problem has a finite optimum solution or it is unbounded. So in a sense now there are no loose ends left out, whatever assumptions we had made, we have done away with them, and we by running this software used for simplex programming, which has phase 1 and phase 2 already included in the program, will give you all the answers. Whatever answer is possible, it will give you that answer. So, I think that sort of brings the simplex algorithm to an end.